Hello friends, welcome to my lecture on subgraphs and traversable graph, multigraphs. Let G be a graph, okay? Then H is a subgraph of G if the set of vertices of H is a subset of set of vertices of G, okay? That is, the vertices of H are also vertices of G, and the set of edges of H is a subset of the set of edges of G. That is, the edges of H are also edges of G. In other words, H V dash E dash is a subgraph of G V E if B dash is a subset of B and E dash is a subset of E. Now, what do we mean by a full subgraph? If H is equal to H B dash E dash, then it is called as full subgraph of G if E dash contains all the edges of E whose endpoints lie in B dash. That is, H is the subgraph of G generated by B dash. So, if H is the subgraph of G generated by B dash, then it is also called as a full subgraph of G. Now, let us consider the graph G equal to GBE given in this figure. Okay. Determine whether or not H equal to H B dash E dash is a subgraph of G, where B dash is ABF, E dash is AB AF. Okay. Now, B dash is ABF and the vertices, set of vertices of G is BG, BG equal to ABCD. Okay. So, since B dash contains ABF and F is not an element of BG, B dash is not contained in B. Okay. Since B dash is not a subset of B, therefore, H B dash E dash is not a subgraph of G. So, it is not a subgraph of Now, let us look at the second part, B dash equal to BCD. So, clearly B dash in the part B, okay, B dash is BCD, it is a subset of B, okay, and E dash consists of BC, this is BC and BD, okay. So, BC and BD, okay, BC and BD. Okay, BC and BD is so the set of BC and BD is contained in E. Okay, so this is E dash is contained in E. Therefore, H B dash E dash is a subgraph of G. Okay, so this is a subgraph of G. Now, then B dash third part C. So, if B equal to B dash equal to ABC, then B dash is a subset of B, okay. E dash is AB AC, okay, but AC is not an edge. So, E dash is not contained in E dash is not a subset of E, because AC is not an edge of AC is not an edge of G. Okay. So, it is not a subgraph of G. Now, let us go to connected components. Let G be a graph, a multigraph. Okay. A connected component of G is a subgraph of G which is not contained in any larger connected subgraph of G. Okay. That means, a connected component is the full subgraph of G spanned by its vertices. Okay. It is the full subgraph spanned by its vertices. Hence, we can designate a connected component by listing its vertices. Okay. It is also clear that G can be partitioned into its connected components. Say, for example, in this case, the connected components are in this graph A C X. We just list the vertices, okay, of the connected components. And then the other connected component is B, okay, this one, okay, which is an isolated vertex, and the other connected component is by Z. So, to determine the connected component is you start at any vertex and then find all vertices that are connected to it. Okay. So, for example, here we started with A and found the other vertices C and A x connected to it. So, that determined the connected component ACX. Here we started with say by, or we can start with Z and then see that by is connected to it. So, by Z is a connected component, and here B is an isolated vertex. So, it is a connected component. So, you can see the graph G is partitioned into its connected components. The graph G consists of 3 connected components ACX, B and by Z. Now, let us find the connected components of this graph. Okay. So, connected, we start with the vertex A. Okay. So, A, D, P, okay, S, C. Okay. The vertices D, P, S and C are connected to A. So, connected component is one connected component is A, D, P, S, C. Other connected component we can say, we can start with B, B, Q, R. Connected components are this and then B, Q, R, and third connected component. So, there are only 2 connected components A, D, P, S, C and B, Q, R. Now, let us go to subgraph G minus B. So, from the graph G, if we delete one vertex, okay, we get G minus B. Okay. So, what is G minus B? G minus B is the subgraph of G, okay, obtained by deleting the vertex B from the vertex set BG, okay, and deleting all edges in EG which are incident on B. Alternately, G minus B is the full subgraph of G generated by the remaining vertices. Okay. So, when you find G minus B from the set of edges EG, delete all edges that which are incident on V, okay, and you will get G minus B. And what is the cut point? A vertex B is called a cut point for G, okay, if G minus B is disconnected. Okay. That means, B is a cut point for any graph G if G minus B has more connected components than G. So, let us look at this graph. Let G be the graph in the figure below, G minus A. Let us remove the vertex A. When you remove the vertex A, you remove all edges that are incident on A. So, you remove this edge, you remove this edge, okay. And what is the graph then left? So, we will have okay. So, this is the graph of G minus A, okay, when we remove A, okay. The 2 edges incident on A will be removed, okay, and G minus B, when we remove B, then this edge, this edge, this edge, they are incident on B. So, they will be removed and we will have so, A, D, E, okay, and we will have C, okay, and we have F, okay. So, this edge and this edge are removed and we have this. So, this is D minus G minus B, and then we have the third part G minus C. So, let us remove C now. When we remove C, they delete C, then this edge and this edge, they will be removed and we will have A, B, C, D, A, B, E, D, okay. C is removed. So, these 3 are, C is deleted. So, these 3 are removed and we have this. Okay, so this is the graph for G minus C. Does G have any cut points? Okay, now we can see we have deleted A, we have deleted B, we have deleted C, and we did not see that there is any A, B, C are not cut points. The graph is not disconnected. Okay, when we delete A, B or C, let us see other cases. If I delete A, B, C, we have deleted. Let us delete D. Okay, so G minus D. What is the graph for G minus D? Okay, so this edge and this edge, they will be removed, and we will have A, B, C, E, F. We can see still the graph is connected. Okay, so D is not a cut point. Okay, and then let us delete E. Okay, so G minus E. When we delete E, this edge, this edge, this edge, this edge, 4 edges will not be there, and we will have D A, B, okay, C, okay, and F. Okay. This edge will not be there, this edge will not be there, this edge will not be, this edge will not be there. So, we have D A, B, C, F, and we can see this graph is connected. Okay. Now, let us see F. Okay, delete F. So, G minus F. So, if we delete F, this edge and this edge will be deleted, and we shall have this graph A, B, D, E and C. Okay. So, this graph is also connected. So, G does not have any cut points, G has no cut points. Now, let us say, let us suppose we delete a edge, okay, from the graph G. Okay. Then let us consider G minus E. So, we are deleting an edge E from the graph of G. Okay. Then the graph obtained by simply deleting the edge E from the edge set of G gives what? See, when you delete the edge, you do not delete the vertices joining vertices of that the end points of that edge. Okay. So, only edge is deleted. So, that means when you delete an edge from the edge set of G, okay, then the vertices of B remain as it is. Okay. So, vertices of G minus E is same as vertices of G. EG minus C will be EG minus the edge E. Okay. So, only edge is deleted, vertices are not removed. Okay. So, BG minus A is BG and EG minus A is EG minus E. Now, bridge for a connected graph. Okay. An edge E is a bridge for G if G minus E is disconnected. Okay. So, after you delete the edge E, if the graph becomes disconnected, then E is called a bridge. Okay. In general, E is a bridge for any graph G if G minus E has more connected components than G has. So, if G minus E becomes disconnected, then G minus E will have more connected components than G. Say for example, this case let us consider G with the graph given in the figure below. Let us delete AB edge from here. So, G minus AB. So, when you delete AB edge from here, what do we get? Okay. The vertex A will be there, okay, and we will have B, C, D. Now, you can see earlier the graph was connected, now it has become disconnected. Okay. It has two components, okay, two components. One is this A, okay, connected components are A and then B, C, D. Okay, so after deleting the edge AB, we see that number of connected components are more than the connected components of G. Okay. Therefore, the here AB is a bridge. Okay. Now, G minus BC, if you remove BC, what we get? This is A, this is B. Okay. BC is removed and we get this. Okay. So, which is not disconnected. Okay. So, since this is not disconnected, okay, this is G minus BC, it does not have any bridge. Okay. Then let us consider G minus BD. Okay. B delete BD. So, we will have okay, AB CD after deleting BD. Okay. It is again a connected graph. Okay. So, there are no bridges. Okay. Then G minus CD. Okay. G minus CD, when you remove CD, what we have? A, B, C, D. Okay. It is again a connected graph. A is connected to B, A is connected to C, A is connected to D. Okay. So, no bridge. So, only the part A. Okay. In the part A, when we delete AB, we get two connected components A and BCD, and therefore, AB is a bridge. Now, let us consider traversable multigraphs. A multigraph G is called traversable if it can be drawn without any breaks in the curve and without repeating any edge. Okay. That is, if there is a path which includes all vertices and uses each edge exactly once, then such a path must be a trail. Okay. And it will be called a traversable trail. Trail is a path where all the vertices are distinct. So, clearly when we are using each edge exactly once, okay, and all vertices, then such a path must be trail, and we call it traversable trail. A traversable multigraph must be connected. Okay. That is clear from the definition. Now, suppose a multigraph G is traversable and that a traversable trail does not begin or end at a vertex P. Okay. So, let us see what we are assuming. A multigraph G is traversable, okay, and that a traversable trail does not begin or end at a vertex P. So, that P is an even vertex. Okay. So, solution is that since a traversable trail enters P by an edge, there must always be an edge. Okay. Whenever the traversable trail enters P, okay, the vertex P by an edge, there must always be an edge not previously used by which the trail can leave P. Okay. So, suppose this is your P point, edge E, an edge is entering here, then because of traversable trail there must be an edge not previously used by which the trail can leave. Okay. So, thus the trail exhausts the edge incident on P in pairs. Okay. So, there will be one edge which enters P and there will be an edge which will be leaving P, and therefore, the P has an even degree. Okay. And so, P is an even vertex. Now, show that a multigraph G with more than two odd vertices is not traversable. Suppose G is traversable and Q is an odd vertex of G. Odd vertex of G means the degree of Q is odd. Then by the above problem, this problem, okay, this problem says that a traversable trail, okay, a traversable trail must either begin or end at Q, because if it does not do that, okay, then the Q must be an even vertex. Okay. So, if G is a traversable trail, Q is an odd vertex of G, then by the previous problem the traversable trail must either begin or end at Q. If it does not do that, then by the previous problem Q must be an even vertex. So, thus G cannot have more than two odd vertices. Okay. So, that is all in this lecture. Thank you very much for your attention.